Doing an ABS fault here on this 2006 Chevy Colorado, and I have the front wheels off the ground already. Our complaint is no left front speed signal, and that was after they did an axle seal. And first thing I'm going to do, I'm showing you scan data here, looking at both wheels. I'm just going to spin the right front wheel, let you guys watch the signal. So you see the right front is making a signal when I move the wheel. Spin the left front, and we have no signal at all. So the first thing we're going to do with this is we're going to determine what type of ABS wheel speed sensors we have, and we're going to check a known good one, which is the right front, and then compare that to the left front. So for this next clip, I've taken some still photos of the right front speed sensor, and I'm going to talk about it and its circuit design, and then we'll come over to the left side and do some tests. First thing when it comes to ABS wheel speed sensor diagnosis is what type of speed sensor do you have? And one of the things that I like to do is a voltage reading on both wires. And I like to pick, for obvious reasons, a known good wheel for my tests. Because if you're checking one of the wheel speed sensors that has a code already, if there's a wiring problem, opens or shorts, that's going to affect your determination on what kind of sensor it is. Now, of course, we can do research too, but in this case, what I did, I took a T-pin, and you can see on both of the wires individually, I am taking a voltage measurement. My black lead is connected to a known good ground. My readings, I had 1.8 volts on one wire, and I had 11.2 volts on another wire. So one of the first things that you need to remember in determining type of wheel speed sensor, whether it be a digital or a AC generating, produce its own voltage speed sensor, is if you have battery voltage, near battery voltage, so 10, 11, 12 volts going to one of the wires on the speed sensor, it is going to be a digital type speed sensor. On digital speed sensors, they do not create their own voltage. They manipulate a circuit and create a square wave. On VRS type wheel speed sensors, which we've used forever, for the past 30 years, we've used speed sensors that are called variable reluctance sensors that produce and make their own voltage. So it would be an AC sine wave. When you see, again, battery voltage, near battery voltage, it is not going to be that type of sensor. So first clue. Second thing would be, which one of these two is the signal wire? We know it's going to be a square wave. Which one is the signal wire? If you look at the two, we have 1.8 volts on one wire and 11.25 on the other. So what I like to do is unplug it, and that will give me a clue as to which one the signal is. And this doesn't always work, but it did in this case. So I unplug it, and with it unplugged, let me find the picture. With it unplugged on the wire that I read 11.2 on, unplugged, I read 11.6. So that, on a digital type, tells me that is my feed circuit. And then on the wire that I read 1.8 volts on, unplugged, I read 0. So that tells me a few things. One, that this is my signal wire, this gray wire right here. And two, it's a pull-up design circuit, meaning the sensor produces this 0 to 1.8 volt reading, or this 1.8 volt signal we had. The sensor produces it, sends it to the computer. So it would be sent down this line. What's producing that? The sensor itself, plugged in right here. Remember, we got a 12 volt feed or 11 volt feed coming in. We're producing that 1.8 volt and we're sending it out. So my signal is that gray wire. We'll pause it here and we'll look at what the signal is supposed to look like on the right front. Before we do the left side, which has the problem, I'm going to show you the waveform on this right front. We know it creates a signal. We talked about its design. It is a digital. So this is plugged in on the signal wire. I'm reading around 1.8 volts, and it would depend on the position of that tone ring on what you're going to read initially with the wheel not turning. And so you can see in that position, I just moved the wheel a little bit. We're reading can't see, 0.69, and move it just a little bit, and then right there, go back. And right there, we're reading 1.837. Go ahead and spin the wheel. This is what it looks like. This is a digital type ABS wheel speed sensor. That is a good looking signal. Good question that was asked of me as we're watching this is what determines the pattern that we're looking at. On this sensor, it's simply going to be the speed at which the wheel is turning, and we're turning this wheel by hand, and we're not turning it consistently. So what you are actually looking at on this screen would be frequency changes which would match the speed at which we're turning the wheel. And if we back up a couple of frames where I just move the wheel slightly to make the signal fixed high or fixed low, depending on where I put the wheel, that's just going to be where the tooth on that tone ring. So there's a tone ring on the axle that's going to have raised teeth on it, right? It's going to depend on where that tone ring is in relation to that speed sensor that's picking up that signal. So tooth aligned maybe is high, tooth aligned is low, I don't know, doesn't matter, but that's what makes that signal stay high or stay low. And so on this type of sensor, I think it's important to note here, on this type of sensor, there are no amplitude increases. Our amplitude, or in other words, our min-max voltage, the min-max voltage is consistent on this design, as opposed to a VRS type speed sensor where what you would see is a signal that would start low and it would increase in amplitude and frequency as you would increase speed. And so this type of sensor is not a very good low speed trigger device, which I believe is why they started using this one, is it's a much more accurate low speed trigger device. So what I want to show you next is a bypass test, and I've shown this in another video. It was actually on a Chrysler, and I'll throw the hyperlink in here for this one so you guys can watch that bypass test I did on that one. And I think the value in this bypass test is going to show itself when we do this left side. What I'm going to do to bypass this is I'm going to unplug the sensor and show you the voltage with it unplugged. Okay, that's with the sensor unplugged. You see we have 0 volts on that wire. And so that is showing us that this is a pull-up design as it was on that Chrysler. What I'm going to do is I'm going to take a test light, and I'm using an LED test light this time because it is a much lower amperage test light, and I'm going to pull the voltage up on this circuit. Okay, what I want to talk about real quick, with this sensor plugged in, I know it's hard to see on this screen. With this sensor plugged in, we're reading 1.8 volts, roughly 1.837, I think I said, on this line with the sensor plugged in on the signal. And then with the sensor unplugged, you see we're reading 0 volts. So here's what I can tell you. I don't know the internal design of this sensor. It's called a Magneto Resistive ABS wheel speed sensor, I think is what the material we read called it. There's a nice video that one of my friends actually on YouTube posted. In fact, I'll put his link in here too for a video that he did drawing the internal circuit designs of this speed sensor. I think it's a really good video, so I'll throw that in here too. But as far as circuit design, pull up and pull down, I want you guys to just keep it simple, okay? We have a computer here, and we have a speed sensor here. And we have a connector that we unplugged, okay? And remember, with this connector plugged in, on this computer harness side, we read 1.8 volts plugged in and 0 volts unplugged. So here's the question, where is the 1.8 volts coming from? Is it coming from the computer or is it coming from the sensor? What this tells us is it's coming from the sensor. And so what I know then is this square wave we're looking at is being generated by the sensor and is being sent to the computer in that direction. And that's why I'm calling it a pull-up design. If this was a pull-down design, what we would see with the sensor plugged in, of course that would depend on wheel position, but to compare the two, we would see 1.8 volts plugged in, and then when we unplugged it, it would stay at 1.8 volts. And what that would tell us is the computer is sourcing that 1.8 volts in this direction, and the sensor is pulling it to ground to make the square wave. And that's not what it's doing. The sensor is plastic. It's a plastic body sensor. There's no ground on that sensor. It has a feed and a signal. It cannot be a pull-down design just by that alone, but this just gives you a little bit of insight in my thought process as to pull-up, pull-down circuitry. Now, why is that important? Well, that's important when you get to the other side, when we watch the rest of this later. And I think I don't want to jump the gun here, but that's important when you're doing bypass testing. If we know this is a pull-up design, that the computer's receiving 0 to 1.8 volt square waves in this direction, if you do a bypass test and you manipulate the circuit with a test light, and we used an LED test light this time, isn't it important to know that so you know what polarity to put your test light to? So we can check the signal circuit integrity, and that's when this becomes very, very important. And of course, also in identifying opens and shorts in the circuit. So let's pause it here and continue watching. There's the connector. See my T-pin still attached to the signal wire. I'm going to take this LED test light that I have connected to battery positive. I'll show it to you when I touch the ground. This light should light. Okay, so touching ground, this LED test light is lighting. I'm going to take the LED test light and I'm going to touch it on and off of this T-pin, which is the signal wire, and it is actually lighting, so it is finding a ground through the computer, but this is very, very low amperage. Again, I mentioned this in the video that the light is lighting. It is lighting because I'm using an LED light, and it does not take very much current flow to light this thing. If this thing finds a ground through the computer, through a resistor in the computer, which it is, that light's going to light. I want to again refer you to my friend's video where he drew the internals of this. He knows it better than I do. That'll really give you a good explanation as to why this LED light is lighting. On some circuits, when we're doing this kind of testing, remember we have a signal wire here that's going to a computer. We're taking a test light to battery positive. If your test light lights, what that's telling you on some circuits is that the wiring is shorted to ground. With an incandescent test light, that probably would not be lighting because that LED is actually finding a ground through a resistor inside of the computer. And again, it doesn't take much current flow. So you see where an LED test light can get you in trouble. We just had an LED test light today tell us that the fuse was good on our data link connector, and it was the wrong pin and it lit, and we thought it was pin 16. It wasn't. So LED test lights can get you in trouble sometimes. This light, what I'm telling you here, is not lighting because of a short to ground. That is not the case. Circuit design, resistor in the computer is causing that light to light. It's normal in this circumstance. What I'm going to do is show you that we can create the signal on the scan tool, and then I'm also going to show you the waveform so you see how much voltage I'm actually putting into this circuit. So I'll get you focused on the screen for this next part. Alright, so I'm holding this connector in my hand. I'm going to rapidly turn it. Oh, actually for this one I don't need to go rapid. I'll show you the voltage levels. This is test light on the wire. We're reading 1.2 volts. Test light off of the wire, we're reading 0.0. So I am not overloading the circuit. I know that was probably some of the concern, me using a non-LED test light in the other video that I did. I really like this LED test light for what I'm doing here, in particular because I'm not exceeding the normal voltage in this circuit. 1.2 volts as a max 0 as a min. Now here, this would be me creating the signal. Remember, the sensor's unplugged, so I'm creating a square wave. Another good teaching moment here is this circuit, what we're doing. We have the sensor unplugged. We're at the sensor connector unplugged. We're connected to the computer still. We have this T-pin. We have an LED test light connected to battery positive. And what I'm showing you right here is we're reading 1.2 volts on this wire. So what I'm doing is I'm feeding 1.2 volts into the computer on this circuit right now. You might be thinking, how are you reading 1.2 volts when that LED test light was lit? Typically, you take a test light like this and you connect it to a ground. That test light's going to light, and this would be 0 volts on the tip of that light. So it really gives you a little bit more insight into this LED test light too. It doesn't need to have a full ground to light. In any case, what we're actually doing, if you think about it like this, our test light is a resistor, and internal to the computer is a resistor before it goes to ground. Now there's a lot more to that circuit, but that's what we're doing. So what we have is a partial voltage drop across this resistor, and then the remainder of the voltage in that circuit will drop across the internal resistor. Now think about this without doing math. If this outside resistor is very, very high ohms, so picture this as like current flowing through the circuit, or water maybe even flowing through a hose. If you squeeze this kink, the kink in the hose, which represents our resistance, if you squeeze that one very, very tight, you're going to have a large pressure drop that occurs right here. We're going to have low voltage in here. The opposite would be true if this one was not a very high ohm resistor and this one was a very high ohm resistor. What you'd have is a pressure back up this way. With high resistance here, we would actually have high voltage in here. And so a little bit of little lesson on voltage and current and how it applies. What we're looking at in this scenario up here is a high resistance test light and a lower resistance internal resistor. So most of our voltage will drop across the first resistor. Not all of it though, because there is another resistor inside the computer. And what were we reading? 1.2 volts. Kind of explains how we use that test light. And I think really the importance of using the LED here instead of an incandescent light, because if we used an incandescent light, we're going to have a much lower ohm resistor out here, and we're going to have much higher voltage remaining in the middle or going to that computer. And I wanted to try to keep the voltage level as close to what the signal was generating in the first place. What I'm going to do now is go back to the scan tool, and we're going to watch this right front wheel right here. This is the one that I'm manipulating. I'm going to do this bypass test. Now again, this is a working circuit. This was a known good speed sensor. I'm just showing how to do a bypass test. And I'm going to, this time I need to do it rapidly because I need to make these signals occur very fast. And as you can see, I was able to make a right front speed sensor signal with my test light. And the nice thing about this test is this confirms circuit integrity from the sensor to the computer is good, and that if you have a good feed voltage to this sensor and unplugged, you do this test and the computer reacts, there's nothing wrong with that signal circuit, you need a speed sensor. Real quick analogy here that might help with one of the previous questions is, what's the computer looking at? What's the computer looking at here? See, we see 14 miles per hour right here. Just give you an idea of how that signal is interpreted. And I'm just going to make this very, very simple here. Let's say that this is a signal that would represent, say, 1 mile per hour. What's a 14 mile per hour signal going to look like? It's going to be the same amplitude. The difference is going to be the signal is just simply much more frequent. And so maybe that's a representation of what a 14 mile per hour signal would look like. How does the computer know when a wheel locks up? Well, there's an algorithm built in that would say we cannot physically go from 30 miles per hour to 0 miles per hour in X time frame. It's physically not possible unless a wheel locks up. So if you're, let's say now this is an example of 30 miles per hour, if that signal all of a sudden flatlines, that wheel just locked up, and then that's how the computer knows which wheel to activate for the ABS system. So let's go to the left side now. On the left side now, and the first thing that I'm going to do is I'm going to T-pin one at a time these back two wires on this connector, leaving it plugged in, and the voltage reading is going to give me some direction. I don't know which wire is which. I don't care. I know I should have 11 point some volts on one wire and 1.8 volts on the other wire as compared to the other side. So I'll just do the first wire and I'll get you down on the screen, and then what I'll do is I'll move this over to the other wire. I don't need to show that part again. This wire is reading 11.3, so that is my feed to this speed sensor, so we know that that circuit is good. Next one, just going to move the T-pin over to the other wire. We know this is a lower voltage circuit, so we can adjust our scales. And that is my other wire, and it's reading 0.02 of a volt. Now remember, with the wheel in certain positions, we had high-low voltage. We could have it low in one position and high in another, depending on where the tooth is on that tone ring. In this case, I'm moving the wheel. We got nothing. So here, I'll spin the wheel now. We had no signal at all on this left side. Now the question here is our wiring on the signal shorted to ground? We know it's a pull-up design. So an open wire is not an option here. An open, we'd have a good voltage signal here and nothing at the computer. Short to ground is our concern, or a shorted sensor. And what we're going to do now is do that same bypass test and see if I can manipulate this circuit like I did the other side and address the wiring issue, and then we can confidently put a speed sensor in this. So what I'm going to do is I'm going to disconnect this connector. And it's important that you're on the correct side. I need to be on the harness side of this connector. So I am on the harness side. I'll get you a shot back up on the wiring. So again, what I'm going to be doing on this side is I'm taking this LED test light to battery positive, and I'm going to touch it on and off the signal wire. Now remember, the light did light on the other side, even though that it was not shorted to ground. So that light is finding a path through the circuitry in the computer. Normal on this, especially using an LED test light. I believe when I used my incandescent light in the last video, it was not lighting because of the resistance in the computer for this circuit, but much lower current with an LED. So the LED test light's lighting. That is not a short to ground. Well, actually it depends what we have on this bypass test. So let me get you down on the screen. I'm going to rapidly turn this on and off, and we're going to watch the reaction. Major concern here is a short to ground with this light being lit. I use this test in other tests that I teach in my book. That take a test light, battery positive, test light lights, circuit shorted to ground, test light doesn't light, it's not shorted. In this case, how do we know that this is not a short to ground? It's real simple. We had a known good side, number one. That helped. Number two, when I did this test, where I'm taking that test light into that signal wire, I also, in the next clip here I'm going to show you, I am monitoring that same signal wire right here with my scope, and I'm going to look at the voltage on that circuit. If this wire was shorted to ground, what we would see on my voltmeter, which is going this way, we would see 0 volts on that circuit. That test light has a full ground. Why? Because it has found a ground in that signal wire. Not the case. What do we have? When we do this test, we see the same as what we saw on the other side, which is not 0 volts on this wire, but around 1.2 volts, which tells us what? It cannot be a short to ground in the wire. We see the same thing we saw on the other side. It's not a short to ground. Very misleading with this LED test light, the fact that that light is lighting. Be careful using an LED test light finding shorts to ground, because an LED test light does not take very much current at all. We might have 100, I don't know what the resistor is in the computer, but it might be hundreds of ohms of resistance, and we're still lighting this light almost like it has no resistance at all. LED test lights. Careful with variables. I guess a final thought, we cannot always rely on a test light to do short to ground testing. Okay, so first thing I'm going to do is adjust my scales. I don't want to be on a 20 anymore. I believe we were on a 5 on the other side when we did it. I'll let you look at the voltage reading here, and I'll show you the on-off square wave that I'm going to make. So holding this on there like we were on the other side, 1.2 volts, a little bit of oscillations here. Why? My test light connection, my ground connection, all very important stuff. It was my ground for my scope is an issue. Always want to check your leads when you're doing work. Check your leads, recheck your leads. Okay, check it again now. There's 1.235 with the test light connected to that. And what that tells me is that signal wire is not shorted to ground. That in itself is really evidence enough. Making the square wave on and off. Of course, at times it's not clean because, you know, I'm tapping that T-pin. Go to the scan tool. Watch my left front. There's my signal, it's already there. On and off on the signal rapidly. You see we can make a signal, no problem. So what that means, without a doubt, our wiring harness is fine. There is nothing else left but the speed sensor in the left front wheel. So really good test, I think, to develop. One of the things I'm learning with these ABS systems is they're not all the same. We just did we did a Jeep Commander 2 days ago that had a similar design, but the signal was not the same. It was actually a 10 volt, 11 volt feed, which actually was the signal. So a little bit different design. The bypass test doesn't work on all of these, but it has proven to be valuable on this 06 Colorado. It was valuable on the hyperlink video that I have in here. I believe it was a 03 Concorde or it was a LHS or some Chrysler model car that it worked very well on too. So digital speed sensor, how to test it, how to determine if it's a digital speed sensor or a analog type, and really the key with that is going to be if you see near battery voltage on an ABS wheel speed sensor wire, that means that is not a VRS type sensor. That means it's a digital type. So that's your circuit identification. And then I showed also how to do a bypass test, which again, super valuable test. I do not need to disconnect the computer. I do not need to ohm the harness, as a flowchart is going to have you do. And you saw that I was only putting 1.2 volts on that circuit through that test light. No danger in overloading that computer. Definitely like the LED test light better than the incandescent for this one. So I hope you guys learned something from that.